Hello everybody, this is Jeff Janess. Welcome to our continuing lecture on surface analysis in ArcGIS Pro, also known as terrain analysis and geomorphology. In our last episode, we discussed what slope is and how it's calculated, and some of the issues we face when calculating slope statistics. We also discussed aspect and how as a circular variable it can be tricky to work with. We looked at several ways to transform aspect into variables that are easier to analyze, and which may more directly correlate with microclimate and vegetation type of the landscape. And in this episode, we're going to finish up our surface analysis discussion by looking at insolation, hillshades, and landscape curvature. But as we prepare to move on to our next topic, let's think for just a second about why aspect is such a useful variable. Aspect obviously has a great influence on vegetation species, composition, structure, and microhabitat, but why does aspect have this influence? Possibly because of prevailing wind direction. If the wind tends to be steady and comes from a predictable direction, then local habitat will be affected by that. However, the main reason why habitat changes with aspect is because of how much sunlight hits the area and at what angle. North-facing slopes tend to be cooler because sunlight doesn't hit it as directly as it does on south-facing slopes. You can feel it yourself. You feel the sun a lot more in your face when you're facing the sun. So if aspect is important because of how it's just a surrogate for sun exposure, then perhaps solar insolation would be a better and more direct variable to use. Solar insolation is all about how much sunlight hits the ground. In many cases, it may be a more direct driver for vegetation and microclimate than aspect. It measures how much sunlight hits the ground based on local topography, and it does incorporate direct sunlight from the sun plus diffuse radiation from the sky in general. It takes a long time to calculate, though. I generated a solar insolation raster of the state of Hawaii once. It took well over a week to finish. Now, the primary outputs of solar insolation are actual measures of energy in kilowatt hours of solar energy per square meter over some time period. If you want to know exactly how many kilowatt hours your study area receives annually, seasonally, or daily, then the solar insolation tools are just what you need. And not only is this interesting information, it also gives insolation an advantage over aspect in that it's much easier to calculate summary statistics from it. You don't need to resort to circular statistics because solar energy is not a circular variable like aspect. And the tool produces interesting optional outputs. You can split the total radiation into direct radiation from the sun itself and diffuse radiation from the rest of the sky. It doesn't estimate at reflected radiation from the ground, which is a shame because that can be high when there's snow on the ground, but you can set parameters for how hazy the sky is, which limits the amount of sunlight that reaches the ground. And one especially cool optional output is the number of hours of exposure to sunlight. This is interesting data, but it also makes a striking image. It's very austere and bleak to my eye, which I kind of like. Okay, our next topic is hillshading. A hillshade is a great way for visually bringing out the shape of the landscape. Basic hillshade uses both aspect and slope to determine how directly any point on the landscape faces the sun. If it faces the sun directly, it's colored white. As the landscape turns away from the sun, it's shaded in progressively darker shades of gray. When you look at the final product, it's as if you're looking down at the actual landscape. The texture of the land pops right out, and it gives your maps a real three-dimensional quality. These days, hillshades are primarily used for aesthetic purposes, but in the past they were also used as an approximation for solar insolation. They wouldn't give you the exact amount of energy hitting the ground, at least not easily. You could come up with a rough conversion factor if you did some research, but they did do a great job of showing the relative amount of sunlight. And it worked, too. I was part of a spotted owl habitat analysis back in the 1990s where hillshade-based insolation jumped out as a highly significant variable. Hardest part was trying to figure out where the sun was positioned at any particular point in time. But these days, the actual solar insolation tools do a much better job for analytical purposes, so hillshades are now mainly just used for the visual effect. And because it's mainly used for making maps look good, there have been many efforts at jazzing up the hillshade to give it even more visual appeal. One of the more popular methods is generally referred to as the Swiss method, after Eduard Imhoff and his contemporaries. And strictly speaking, the Swiss method is a manual method of hillshading where the cartographer draws the shadows by hand. Now, Kurt Brassel introduced some automated methods to replicate some of the best qualities of the hand-drawn Swiss method, specifically recommending 3 general modifications. First is hypsometric shading, where you make the lower elevations darker than the higher elevations. Second is generating hillshade where the sun is placed in more than one position. And third is to blur the hillshade a little. Okay, let's discuss these in some more detail. And first up is hypsometric shading. I like this effect. It makes the lower elevations darker, so they just appear deeper. Kind of what you'd expect the landscape to look like at dusk and dawn, which I think are the prettiest times of day. It gives kind of a gloom to the lower elevations. To me, at least, makes the landscape look more mysterious and magical somehow. That just makes the map more fun. Effect is easy to achieve, too, and I'll demonstrate it in one of the labs. Basically, you just take a DEM, shade it from black at the lowest elevations to white at the highest elevations, set it to be partially transparent so you can see through it, and then place it on top of the hillshade in your map. The next Swiss method effect is to generate your hillshade using more than one light source. The basic hillshade tool just asks you to specify a single point in the sky for the sun location. Generally looks pretty good, but people have noticed that this single light source sometimes causes some topographic features on the map to get kind of washed out. They get illuminated the same even though they face in different directions. And people have come up with some creative ways to generate light from more than one direction to overcome this issue. And this fellow Kurt Brassel recommended setting a variable light source direction for each cell based on a primary illumination direction plus a directional adjustment computed from the slope and aspect of that cell. By Brassel's method, every cell in the hillshade raster could receive a hillshade value that was based on a different illumination angle. That's a little tricky to do. There's no standard tool that'll do that. You could get to it if you wrote code to do the hillshade yourself, but outside of that, it's kind of not available to most of us. A much easier method is to just generate 2 hillshades of the same area, but with the sun angle set to different places. Then add the 2 hillshades together using the raster mathematical tools we've discussed earlier. Eduard Imhoff suggests this method in his book, using 2 light sources separated by a small amount, like 10 to 15 degrees. In this example here, I've generated a hillshade with the sun set at 2 locations 90 degrees apart, one at 270 degrees due west, and the other at due north at 360 degrees. Then I added them together, and this does appear to bring out a few details of the landscape that aren't captured by the single hillshade. Now, there is an interesting and more sophisticated way to do this called the multi-directional oblique weighted hillshade. It's usually referred to as the MDOW hillshade. It's invented by a fellow named Robert Mark with the USGS back in 1992. It creates an interesting effect and does a better job at bringing out details on the landscape surface than a simple hillshade. To me, it makes the landscape look kind of glossy. Now, MDOW uses 4 illumination sources, and then it weights the strength of that illumination based on how directly the landscape faces it. Interestingly, it gives the illumination the most weight when the landscape is facing perpendicular to it, and the least weight when the landscape is facing directly toward that sunlight. Thus the name oblique weighted. And you can see the weighting system in this graph. The direction values here don't mean compass direction, but rather how directly the landscape faces the illumination source. 0 degrees means the landscape is facing it directly. And you can see that the weight applied is 0 at this point. The illumination is effectively turned off if the landscape directly faces the source, and dialed up as the landscape turns away from it. So the strength of the light source is maximized when the landscape is at 90 degrees counterclockwise and 90 degrees clockwise to the light source. When generating an MDOW hillshade, you specify the general illumination direction, just like you do in a normal hillshade. Then the MDOW algorithm arranges the 4 MDOW illumination sources around that primary direction, spaced at 45-degree intervals. You essentially generate 4 separate oblique-weighted hillshades. And in this graph, we set the 0 degrees to be the direction of the general MDOW illumination source, and the first light source is set at 67.5 degrees counterclockwise from the primary direction. Weighting scheme for the first light source is distributed like this. Then we add a second light source centered at 22.5 degrees counterclockwise from the primary illumination direction. This is 45 degrees from the first light source, and these weights are distributed like this. Then we add a third light source at 22.5 degrees clockwise from the primary source, and finally the fourth light source at 67.5 degrees clockwise. Now, here we go. This is another example where a standard Cartesian graph doesn't really show the circular nature of the data, so we usually present this as a circular graph, similar to the rose plot graph we saw earlier. And here we see the primary direction of the light source, the direction of the 4 MDOW components distributed around that primary direction, and the weighting factors for each component. The graph's a little confusing the first time you look at it, but it's pretty cool once you realize what it's saying. But the basic steps are that we first generate 4 hillshades from these 4 directions. We multiply the hillshades by these weighting factors, and you get the weighting factors by calculating the deviation of aspect from the direction of the hillshade. Then you take the sine squared of that, basically means to subtract the hillshade direction from the aspect value, take the sine of that, then square the sine. So now you've got a raster of weight values for this hillshade. Multiply the weight raster by the hillshade raster for each of the 4 hillshades and add them up. Now that was kind of quick, so if you're interested in trying this out, we're going to do it in an optional lab exercise, so you can see all the steps there. Okay, so we've covered 2 components of the Swiss method. First is hypsometric shading, secondly setting the sunlight at different sources, and the last component of the Swiss method for hillshades is to blur the landscape a little. USGS does this on the online topo maps. And as I switch back and forth between the USGS map and a pure hillshade, you can see the details in the pure hillshade that are washed out in the online topo map. People who like this option like the fact that it makes the hillshade effect more subtle, and it washes out artifacts and errors in the original DEM. Now, the original purpose for blurring the landscape was a lot more appropriate for the time. As Brassel shows in his manuscript from 1974, the printing methods available at that time were just not as sharp and clean as they are today. So Brassel recommended that the printed hillshades be actually photographed and manually blurred in order to get rid of that dot pattern. So if you choose to blur your hillshades, make sure it's because you like the effect. Don't do it just because it's always been done, because the original reasons really don't apply today. I personally lean toward sharp and crisp hillshades like you see in my video backgrounds, where others prefer to blur them a bit. Fortunately, you have the artistic license to use whatever method you like. It's easy to do if you want. Best way is just calculate a neighborhood mean of your DEM using the focal statistics tool, and we saw how to do that the last lecture. This essentially blurs the DEM. Then you generate a hillshade from that blurred DEM. You get a blurred hillshade. And one last comment on hillshades. In the northern hemisphere, the sun usually shines from a southerly direction. However, the hillshade tools by default place the sun in a northerly direction, specifically in the northeast at a 45-degree inclination. Why is this? Why, by default, put the sun in a position it never actually occupies, or at least for people in the northern hemisphere? The answer is interesting. Take a look at this image. Do you see this line through the middle as rising up or sinking into the ground? Most people, and I believe the numbers are somewhere around 80%, see this as a ridge line rising up from the landscape. Not everybody, but certainly the great majority. However, this is just an optical illusion created by placing the sun in the south. Or, in other words, to place the sun where it actually exists relative to the landscape. The effect is magnified if we put an inverted hypsometric shading over it. Now, if we switch the sun position to the north, where the sun never actually is, then most people correctly interpret this as a canyon. Specifically, it's the Grand Canyon in northern Arizona. Now let's turn to our last surface analysis topic, landscape curvature. Now, curvature can be used for many purposes. In fact, there's a lot of ways to define it. There are versions that tell you generally how bent the landscape is at some point. Other options that also tell you how bent it is, plus whether the landscape is convex like a hill or concave like a valley. Some of the most commonly used types of curvature are often used in hydrologic analysis to tell you whether water will converge, diverge, accelerate, or slow down as it flows over a point. Let's start with the versions that are commonly used to describe water flow. These are some of the most commonly used measures of curvature in ecological applications, and they describe conditions that affect a lot of things other than flowing water. but the flowing water concept is a good way to visualize and understand what they mean. And first, let's understand what these types of curvature are really measuring. It's not the general curve of the landscape, but rather the curvature of a line crossing the landscape surface. This line represents the intersection of a flat plane with the landscape surface. If you imagine a geometric plane cutting into the landscape, then this line is where the plane hits the surface. Then the curvature value at a point is telling you how bent the line is at that point. So the question becomes how to orient the plane. If we place it in different positions, we can learn very different things about the landscape. For example, if we use a vertical plane and we aim it in the direction of steepest slope, that's the direction of aspect, then we get what we call the profile curvature. Profile curvature tells us whether the slope is getting steeper or more gentle at that point. Positive values means it's getting steeper, and therefore water would be accelerating as it flows over the point. Negative values means it's getting more gentle, and therefore water would be slowing down as it flows over the point. Now, quick word of warning regarding these positive and negative values. You should know that ArcGIS Pro has two tools that'll calculate curvature. They have one called Curvature that uses algorithms that go back many decades, way back to the days of ArcInfo, ArcView, and ArcMap. Recently, they've come up with a new tool called the Surface Parameters tool. Now, in the original Curvature tool, which is still available in ArcGIS Pro, positive values for profile curvature meant a concave surface where water would slow down, and negative values meant convex where water would speed up. The new tool reverses these values, so that positive values now mean a convex surface where water speeds up, and vice versa for negative values. So be aware of this if you end up using both tools, or if you get data from someone who used a different tool than you did. There's a lot of potential for confusion here. Okay. Now, let's move on. If we orient the plane so that it's flat, meaning that every point on the plane is at the same elevation, we get what they call plan curvature. You might notice that the intersection line between a flat plane and the surface is basically a contour line. So plan curvature is the curvature of that contour line at a point. Positive values mean that water would diverge as it flows over that point. Negative values means that water would converge, like at the bottom of a drainage. Relatively high positive values may also indicate ridge lines or more exposed places on the landscape, while highly negative values may indicate drainage bottoms or places more protected from the elements. And plan curvature is very cool because it tells us the curvature of contour lines, which makes it an intuitive measure for many of us. However, the internal algorithm that calculates plan curvature can create extreme values when the landscape is very close to flat, but not quite exactly flat. Plan curvature values are generally near zero, rarely getting higher than 3 or less than -3. And if you have a slope of 0, then plan curvature will be 0. However, if you have a slope that's just tiny fraction, less than a 10,000th of a degree, then all of a sudden your plan curvature values shoot up into the thousands or down into the negative thousands. Now, it's not really a huge problem for most of the landscape, but it does make it much more difficult to symbolize this data for your maps because these extreme values skew the color ramps so much. Now, one solution to this problem is to orient the plane so that it basically sticks out straight from the landscape in the direction of steepest slope. If we do this, then we get what they call tangential curvature. Tangential curvature is pretty similar to plan curvature in how it predicts whether water will converge or diverge as it flows over the landscape. The algorithm's a lot less prone to generating those extremely large values when the landscape is nearly flat, though, so tangential curvature is a lot easier to display in a map than plan curvature. Okay, so we've discussed these 3 cases where we intersect a plane with the landscape surface. Then we define curvature as a curvature at a point on the line of intersection between the plane and the landscape. So you might be wondering, well, what are these curvature values saying exactly? What are the units? If a curvature value is equal to 0.2, then this means 0.2 what? Well, let's clarify this because it's not an obvious answer. In general, curvature values are reported in units of the reciprocal of the radius of curvature. So what's that? Suppose we have 2 points on the line at A and B. In this example, we are measuring the landscape in meters. Now, clearly, just looking at it, point A has a higher curvature than point B. You can see the curve is sharper. So how do we quantify that? Start by imagining that the line does have some particular curvature value at that point. If we extend a line following that single curvature value, we're going to get a circle. Once we've got that circle, we'll have a small circle for point A and a larger circle for point B. We calculate the radius of that circle, in meters in this case because we're measuring in meters. The circle at point A has a small radius of 0.8 meters. Circle at point B has a larger radius of 2.5 meters. In each case, this is what we call the radius of curvature for that circle. We take the reciprocal of that, basically dividing 1 by that value, and we have the curvature units. In this example, if the smaller circle has a radius of 0.8 meters, then the reciprocal would be 1 over 0.8 or 1.25. Point A has a curvature value of 1.25. Circle at point B has a bigger radius, 2.5 meters, so the curvature at point B is 1 over 2.5 equals 0.4, which is a much smaller number than the curvature at point A, indicating that point B has a lower curvature value. Now, another quick word of warning regarding the two curvature tools available in ArcGIS Pro. Because landscape curvature values calculated from coarse DEMs, and by this I mean like 30-meter resolution or larger, then, well, these curvature values tend to be very close to 0. The original version of the tool would multiply the final curvature values by 100. The new tool does not. Therefore, the original tool produces curvature values that tend to be about 2 orders of magnitude larger than the new tool. They also use slightly different algorithms for plan and profile curvature, so the numbers will rarely be exactly the same, even accounting for those 2 orders of magnitude. So please be aware of this if you use both tools. Just another possibility of confusion there. Now let's take a look at a few of the other ways you can calculate curvature. These are more general measures of how the landscape surface itself is bent, rather than the curvature of a line laying across the landscape. First up is mean curvature. This value can be both positive and negative. It's actually calculated as the average value of the profile and the tangential curvature values, since both tangential and profile give positive values for convex surfaces and negative values for concave surfaces. Well, a large positive mean curvature value is likely to be convex in both the tangential and vertical planes, and large negative value is likely to be concave in both planes. As such, it might be a good indicator of exposure or protection. High positive values would also indicate regions that are most likely to erode because they're sticking out from the landscape, while high negative values would be places where eroded materials would be more likely to accumulate on the landscape, sort of at the bottom of a hill. Okay, now similar measures the Gaussian curvature, which can also be positive and negative, and which generally indicates how bent the landscape is. Positive values are convex, they indicate hills or ridges. Negative values are concave, and they indicate dips, valleys, sinkholes, or anywhere that the landscape bends inward. Now, if you're only interested in how bent the landscape is, and not whether it's convex or concave, well, then you might want to try the Casorati curvature. Casorati curvature values start at 0 when the landscape is not curving at all, and it increases as curvature increases. Another possibility, you could just take the absolute value of the Gaussian curvature. Both would kind of capture that concept of generally how bent it is. All right, well, I think that's a good stopping point for this video. We've covered insolation, we've covered various methods of hill shading, and several flavors of curvature. So in the next video, we're going to discuss a few issues to consider when working with raster data, and discuss a few ways to avoid common problems with the raster tools. Thanks so much for watching, everybody. Take care. Bye-bye.